Hey everyone, in this video we are going to be looking at one of the problems that we tried to solve in class. In this problem you'll notice that we have a beam, and on this beam we have three external forces. What we are meant to do is basically calculate the moment about point A. Now you might have noticed that I changed this from point B to point A. That's because if you do so, it's probably easier to calculate it compared to A. So I prefer to calculate the moments about point A. So I've already redrawn the example on here, and what I'll be using is basically the principle of moments equation, and that states that the moment is equivalent to f of x multiplied by dy plus fy multiplied by dx. This applies if you have a force and you want to find the moment through its components. But if you notice in here we have three forces, so 1, 2 and 3, and that means that we have to apply this 3 times the equation in order to find the moment. So what I will do is I'm going to say for moment 1, it will be f of x1 times d1 plus fy1 times dx1. So that means that for this force, its x component will be multiplied by a y distance or perpendicular distance, and the y component of this force is going to be multiplied by an x distance. Now if we decompose this force, we basically end up with, let's try this one. So this is f1. Its components are going to be, that will be your f of x, and this will be your f of y. And let me just add some text on here. So this will be fx1 and then this one down here will be fy1. Okay. Now, if you notice that the angle is actually between the force and the y-axis, so basically the angle down here is going to be 30. Usually what I want is basically the angle in here so that I can standardize my solution based on what I've been teaching you for the past few weeks. So the angle between the x-axis and the force will be 90 minus 30, which is the angle between the y-axis and the force, and that means that this angle is 60. Now I can use my equation, which states that for fx1 it will be the force multiplied by its cosine of 60. So if we replace f1 with 250. That means that I get 250 times cosine. So I get 125 newtons. So that's fx1. And then I'll do the same for fy1. fy1 is going to be multiplied by sine 60. 250 times sine 60, I get 216. 216.51 newtons, 2 decimal places. Okay, now I need to find dy1 and dx1. So let me put this up here because that is the general equation. This is the equation we're using for moment 1. Let's put these up here. That means that for dy1, if I look at the force is in here, the point is somewhere down here, right? Which is point A. So if I again illustrate this, so point A is somewhere around here. That is A. And technically, this is the line of action. What that means that for fx1, if you look at the force, it's basically the point of application is somewhere down here, which means f of x1 should be somewhere down here, like so. And now if you look at this line, the line of action of fx1 is passing through this dashed line, and that means that for f of x1 it's basically trying to push a point A, and that means that there's no moment, so there's no rotation technically from fx1. So that means that dy1 is equal to 0. Now if we look at fy1, it is perpendicular on this dashed line, and that means that it will generate a moment or a rotation movement. The distance between fy1 and A, which is dx1, is equivalent to 2 meters. So what I will do is say that f of x1 times dy1 is basically 125 multiplied by 0, and you get 0. For fy1, it will be 216.51 multiplied by 2 meters. And if you multiply this by 2, you get 433.01 Newton meter. Now, we're missing one thing, which is the direction of this. Is it counterclockwise or is it clockwise? And if we look at how fy1 is rotating about A, it's going clockwise. That means that this value is actually a negative value, like so. And that means that this is also a negative value. So that is m1. I'm just going to put this up here because I want to get rid of all of this so that I can work on the next force, which is F2. Actually, let me just get rid of this one. And so for M2, it will be f of x2 times dy2, and then all of these just change them to 2's. Here, that's the force. This is the horizontal or x-axis, and we're given the angle. Perfect. I don't need to do like what I did in here, which is try to find the angle between the force and the x-axis. So what I will do, this is sort of straightforward, is basically multiply 300 by, again, cosine 60, and that should give us 150. And for Fy2, it will be 300 again, multiplied by sine 60, and this will give me 300 times sine 60 to 259.81 newtons. Right. So if I draw this force, it's going downwards like so. Its x component is going in this direction, and its y component is going downwards in this direction, like so. We need to find the dy and dx. Again, this is the point of application where the external force is applied, and this is where point A is, somewhere down here. Now, if that's the point of application, then technically, technically this force is being applied down here, and this force as well is being applied like so. But let's focus on f of x for now. Let's get rid of this one. If you notice that what the force in the x direction is doing is basically passing through this dashed line, which means its line of action is within this dashed line, and that again means that its dy is equal to 0. So we can exclude this from the moment calculations. For this, so let's get rid of that one. For this force, that's the point of application, and if you look at the line, it's basically having a perpendicular distance on the line, which means it does have an x distance, and its x distance is equivalent to 3 plus 2, because that's the distance from here all the way to there in the x-axis. So taking that into account, let me just copy and paste. So again, this will be 0, 0, and this will be 259.81 multiplied by 5. So 259 times 5. And this gives me 1299.04. Once again, don't forget the units, Newton times meter. Once again, this is going clockwise about point A, like so, which means that it's actually negative in here. That means that the result will also be negative. And so I'm just going to put this on the side up here, and then move on to the next question. The next part of this question. Let me get rid of this one. Okay, so the next one is F3. So I'm just going to draw another arrow. F3 is pointing in this direction. Its x component is in this direction. and its y component is going downwards like so. So the equation then becomes m3 equals to f of x3 dy3 fy2 fy3 and dx3. Let me get rid of these lines. Okay, now we have this triangle thingy, and to calculate the angle, you can literally find the angle using the sine inverse, which we learned in class, or there's a simpler way of basically calculating the force, and it is basically using the trigonometry relations in order to find the x and y components of the force. So for fx3, it will be the 500, which is f3, multiplied by, we want cosine, so that means that it will be 3 over 5. So the adjacent over the hypotenuse, which is 3 over 5. And this will give me 500 over 5 is 100, 300 newtons. Let's do Fy3. Again, similar case, so 500. The opposite is 4. Obviously, we're looking for the sine now, which means it's basically 4 divided by the hypotenuse, which is 5. So again, that will give me 400 newtons. So we found these two. We need to find dy and dx. Now, if you look at where so if we reapply this, or if we just look at the whole beam, this is the point of action on the beam by F3, and point A is all the way up here. So that means that to find dy, it will be the distance from here to here, and that means it's 4. So dy is equivalent to 4. Let me just write this down. 4 meters. For dx, it will be the distance from here to there, and that distance is 5 meters. We've already determined these, so that is 300, and this will be 400. Another thing we need to take into account is the signage, or the signs. If we look at how, let's start with f of x3. So that's f of x3. It's basically going clockwise, so that is a negative value. This one is again going clockwise, so that again is a negative value. And we end up with, let's see, so that is 12, and that is 23,200. Yeah. And don't forget the unit, which is Newton meter. Don't forget the sign. That's very important. Okay, so these are the moments that we determined from each force. What we need to do, which is add an extra step and say, let me get rid of these, and that one, and this one as well. I'll just say that the moment at point A equals to And we're just going to add all of these moments. Negative 433.01, negative 1299.04, negative 3200. And technically you should get 1299.04, 433.01, and you should get 4932.05 Newton meter. And that should be the correct answer. Okay, thank you for watching. Bye.